For a long time, it was believed that the movement of galaxies was a natural reflection of the universal expansion. But recent measurements have revealed something that doesn't fit into any known formula: a constant, directed, and precise acceleration. As if a silent force were realigning all of space around us. Instead of a scattered universe, what we observe is a flow, a continuous displacement that drives entire structures toward a hidden coordinate. Nothing in it is random. Nothing in it is chaotic. There is a pattern, and it points to an origin that science has not yet been able to identify. What is most unsettling is that this pattern repeats itself on such vast scales that it challenges the idea of cosmic autonomy. The Milky Way, the local group, the nearby superclusters, all follow the same direction, like pieces of a mechanism that operates far beyond any human comprehension. And the more instruments manage to penetrate the opacity of the Milky Way, the more evident it becomes that the universe is not just expanding, it is being pulled. If there exists an entity, structure, or process capable of moving thousands of galaxies simultaneously, its nature resembles nothing that modern astronomy has catalogued. What lies behind this continuous acceleration is not merely a colossal mass. It is a force that alters the very fabric of the cosmos, and we are traveling toward it without any possibility of choice. As new measurements of galactic motion accumulated, it became evident that the observed acceleration could not be attributed solely to universal expansion. The Milky Way's movement does not exhibit the irregularities typical of local gravitational interactions, but rather a continuous, stable, and persistent trajectory. This indicates that forces act upon it on a scale that surpasses any known structure. The direction of this movement coincides with a region of the sky obscured by the galactic disk itself, creating an observational silence zone that delayed the understanding of the phenomenon for decades. With the advancement of instruments sensitive to high-energy radiation, this previously invisible area began to reveal traces of extreme density, associated with gigantic structures buried behind cosmic dust. Although some of these structures have been identified, their combined masses still do not explain the speed at which the Milky Way moves. This discrepancy, repeated in independent measurements over the years, points to a gravitational deficit that cannot be ignored. The presence of an additional force or structure becomes inevitable. The interpretation of this pattern, when connected to studies of supercluster flow, suggests that the Great Attractor is not an isolated event, but a piece of a much larger system, a silent reorganization of space in which thousands of galaxies follow a common vector. Understanding this movement means admitting that there are regions of the cosmos whose influence has not been catalogued and whose properties may not be limited to conventional matter. It is in this context, between incomplete data and persistent anomalies, that the Great Attractor emerges as one of the greatest conceptual challenges of contemporary cosmology. When the first detailed surveys of the peculiar movement of galaxies were compared, a pattern emerged that contradicted decades of theoretical expectations. The recorded velocities were higher than predicted, even when all possible sources of local gravitational influence were added together. There were no irregularities that could be attributed to random interactions. Instead, an unsettling coherence was observed. Structures separated by millions of light-years exhibited similar accelerations, as if responding to an invisible order. This uniformity made no sense within a homogeneously expanding universe. Analysis of these movements revealed that they converged on a specific region located precisely behind the Milky Way's disk, where stellar dust blocks direct observation. For a long time, this coincidence was treated as a technical obstacle, until instruments sensitive to high-energy radiation showed that the obscured area was not simply a hidden space, but a sector densely filled with supermassive structures. However, even when accounting for all the galaxies identified there, the amount of matter was still far below what was needed to justify the recorded acceleration. This persistent deficit amplified the feeling that something fundamental was being ignored. What made the phenomenon even more intriguing was discovering that the Milky Way's movement was not an isolated case. Several neighboring clusters exhibited the same pattern, all being pulled in the same direction. This large-scale synchronicity indicated that the Great Attractor could not be treated as a local anomaly, but as a gravitational agent distributed over a much larger region than previously imagined. It was as if the universe were orchestrating a silent flow, directing thousands of galaxies without leaving any visible signature of their true origin. As X-ray and microwave-based detection technologies penetrated the previously invisible zone, it was revealed that massive structures were compacted in that region. Some of these clusters have sufficient density to deform the flow of matter around them, but even combined, they do not justify the total acceleration recorded. This discrepancy between observable data and the values predicted by standard gravity fueled the hypothesis that a substantial part of the influence exerted there does not come from luminous matter. The region appears to be a point of convergence where gravity intensifies beyond what is expected, suggesting the presence of components not directly detectable. The discrepancy deepens when we observe that the movement of increasingly distant structures also points in the same direction. Superclusters that should be following independent trajectories exhibit a persistent gravitational alignment. This implies that the acting force is not centralized in a single object, but spread over a large spatial extent. The magnitude of this influence suggests that we are facing a distributed concentration of mass, possibly a dark matter mesh on an unusual scale, or even a continuous distortion of space-time that does not behave like conventional mass. With this set of evidence, the Great Attractor ceases to be interpreted as an isolated entity and begins to be seen as part of a much broader structure. It may represent just one node in a gigantic gravitational system, in which multiple massive regions act together. The nature of this interaction challenges classical models, requiring explanations ranging from unusual dark matter configurations to cosmological phenomena that have not yet been formally described. With each new observation, the hypothesis of a dispersed gravitational agent is strengthened, reinforcing the idea that we are embedded in a field whose workings remain partially hidden. As more distant observations were incorporated into cosmic flow models, it became evident that the perceived gravitational influence was not restricted to the nearest clusters. Structures far beyond the Virgo supercluster also exhibited aligned motion vectors, even though they were separated by hundreds of millions of light years. The coherence of this pattern reveals that we are not dealing with a local phenomenon, but with a large-scale reorganization capable of altering the velocity distribution of entire portions of the observable universe. This synchronicity makes any explanation based on isolated events improbable. Analysis of this dynamic led to the identification of Laniakea, an even larger supercluster encompassing the Milky Way and hundreds of thousands of other galaxies. It functions like a kind of tissue-like structure, where gravitational filaments organize the distribution of matter into large corridors that guide these galaxies along defined paths. However, even this expanded description does not fully explain the direction and intensity of the observed movement. The flow does not appear to follow only the mass distribution within Laniakea, suggesting that its main influence may be connected to an even larger and not fully mapped structure. The persistence of this directed flow raises the hypothesis that the Great Attractor is only a partial manifestation of something deeper, a gravitational convergence that extends beyond the current range of detection. Some models simulate this region as a depression in the gravitational potential of the universe, where forces distributed over a vast expanse create a gradient capable of moving entire galaxies. This approach suggests that the phenomenon is not an object, but a process, a collective effect of invisible structures that shape the cosmos on scales that are still beyond human observational capacity. What is perceived is only the surface of a much broader mechanism. As advanced models attempted to reproduce the observed gravitational flux, a disturbing finding emerged. Even with all the catalogued structures, even adding the estimated dark matter, a significant amount of mass was still lacking to justify the recorded acceleration. The discrepancy is not small. It is so large that it directly compromises the foundations of classical gravity on cosmological scales. The Great Attractor ceases to behave as an isolated region and assumes the role of a systematic deviation in the behavior of the universe. The data not only defy explanations, they point to a presence whose nature remains completely undefined. Given this inconsistency, some models have begun to consider the possibility that the Great Attractor does not represent a concentration of matter, but a profound alteration in the gravitational potential of space-time. In this scenario, what we perceive as a pull would actually be a gradient in the very fabric of the universe, where extensive regions of low energy create preferential gravitational paths. Gigantic structures would not be attracted to a point, but sliding along an invisible cosmological inclination. If this hypothesis is correct, it suggests the existence of a still undescribed mechanics that operates silently over billions of years, reorganizing the architecture of the cosmos. The most unsettling implication is that this dynamic doesn't depend on conventional matter and may have no defined limit. In some models, the gravitational tilt extends beyond the observable universe, suggesting that our cosmic region is just a fragment of a much larger system. The emerging feeling is that the Great Attractor may be merely a local symptom of a vast and continuous process whose origin lies beyond the reach of current instruments. What we perceive as movement is not an exception. It is the rule, and we are bound by it. Even though the phenomenon remains shrouded in uncertainty, the continuous movement of an entire region of the universe demonstrates that we are still far from understanding the totality of the forces that shape the cosmos. Each new measurement, each discrepancy, and each anomaly reinforces the idea that we are only observing the outlines of a much larger mechanism whose extent surpasses our current capacity for detection. The acceleration that leads us towards the Great Attractor is constant, silent, and inevitable. A reminder that the universe operates according to dynamics that disregard theoretical limits or human expectations. This scenario should not be interpreted as an omen, but as an opportunity for investigation. Science advances precisely when it encounters phenomena that do not fit the prevailing model, and the Great Attractor represents one of the most challenging frontiers of this process. Each question formulated, each hypothesis discarded, and each new observation expands our understanding of the deep structure of space-time. Continuing to explore these anomalies is essential to deciphering what lies hidden beyond the observable region, and perhaps understanding why the universe is organized in this way. If you want to continue following analyses that investigate invisible phenomena, colossal structures, and mysteries that challenge current theories, subscribe to our channel and leave your comments below. This directly contributes to the production of content that deepens the scientific debate and keeps alive the interest in topics that are still far from being completely resolved. There is much more to be discovered, and each new question can be the starting point for a broader understanding of the universe.